И наш следующий докладчик Кристофер Траверс.
Our next presentation will be from Mr. Christopher Travers about the Bagger application for massive log management on PostgreSQL.
Thank you all for coming. Now, the slide does say Felix Vishka as a co-author. He is one of our maintainers of this project at Adjust, but in this presentation, I'm the one giving it. So, first, it's worth giving some context before I get started. Who are we? What do we do? Why do we have so much data? Adjust, the core of our business is mobile advertisement attribution. So we track clicks on ads, and we track purchase behavior from applications, and we allow people who develop applications to determine how profitable their advertising campaigns actually were. As well as to allow people to purchase advertisements on a per acquisition or per user basis. We're a trusted third party. We referee these contracts, and as a result, on the analytics side, we see a very large amount of traffic, roughly maximum somewhere in the order of 500,000 requests a second. So about me, I head the database department at Adjust. I've been a software developer and Postgres user for now somewhere around 21 years. I have more experience than most people in this room. Maybe there are some who have more than I do, I don't know. I did have Felix check the accuracy on these. He's one of our platform engineers, and he's the current maintainer of this Bagger system. So that's a picture of a machine called Bagger. I think it's Bagger 268 or something, or 286 or something. It's basically a big machine that tears apart the ground, puts it on a big conveyor belt, and eventually dumps it either onto the ground or into train cars. It's used mostly for coal mining. We named our log management system after these machines, and it's actually a pretty good metaphor for how we go about doing things. Our data storage, though, is entirely on Postgres. So basically, we need to be able to provide information relating to client tech support requests. Did you send us callbacks? What did your servers see, in terms of our advertisement activity? And so we have a whole lot of stuff to log. We rarely have to look at it, but we do have to look at it. It's stored for about no more than 30 days, usually less because we run out of disk space. And it's just a generalized debug application log for data from somewhere around 100 or more servers, probably 100 to 200 servers. Previously, we were on Elasticsearch, and 2 years ago, my colleague Victor Brodlo stood at this podium and talked about why we moved from Elasticsearch. We had over 1 petabyte of data at the time. It was hard to manage. It was really easy to crash. You could exceed the Java heap, and Elasticsearch would happily run the query on the next node and basically do that until you lose quorum, and then you're stuck. And near the end, we did not have very many successfully returned queries. We could load data in, but it was basically write-only storage. Write-only storage is bad. So I want to talk about what we replaced it with and what we did on PostgreSQL, as well as the open source tooling that we've currently open sourced and what we're trying to open source now, as well as some of the difficulties in doing so. Our overall architecture is like this. We have data comes in, it's written to Kafka, which is basically just, you can think of it as basically like Unix streams, but persistent. We have a program called Shuffle, which I will talk about in a moment, which basically loads data into 2 duplicate databases. We do not use binary replication, we just simply load it twice. And then we have a master database that is used by a query application to be able to go out and query all the different Postgres instances we have, because nobody wants to write a bash loop that goes through 750 Postgres instances and pulls back data for you. So the master database just basically stores what nodes we have for restoring data, what Postgres instances are in each of them. It tracks usable partitions for each time period and other criteria. And we partition this by hour, by service, and by tag. So when we send callbacks to clients, we store that separately from the inbound data. And then, again, we separate these out by hour. So each partition contains no more than 1 hour worth of data. They're retained for as long as we can, and then we drop them. Structure of the database, it just has 3 tables. One is backends. These are the actual Postgres backends. The second is partitions, so we can tell which backends they are. And we call it master and slave, despite the fact that always there's some politics about labels. That's actually a really bad set of terms in this case, because we independently write to both. There is no master, there is no slave. They are co-equal, just copies. And finally, we have generation, so when we add servers, we can remap things and keep things up to date. On the data nodes is where we start to do things that are interesting. Each data node has between 8 and 10 Postgres instances. The old ones have 8, the new ones have 10. We use ZFS for data storage, and we do it for one very simple reason. These systems are optimized solely to load data. They are not optimized for querying it. They will query it, but it's somewhat slow. But we load data literally as fast as we can. With ZFS, we can compress our writes, and therefore, because we run these onto hard drives, we can basically cram more through the same linear writes on the drives. Each Postgres instance has 2 data schemas, one for the primary and one for the mirror. Again, primary is a bad term here. They're co-equal. And then shuffle writes to both of them. There's one extremely important detail that I did not put on the slide that I want to mention. It is also one of the biggest mistakes we made when we designed this. ZFS is absolutely terrible once you start adding auto vacuum. So we turned auto vacuum off. I will get into why this is a problem in a few minutes, and the kinds of problems that we had from that design decision and what we have to do about it. So, Shuffle is an open source tool we've written. That, by the way, is the kind of shovel that Bagger uses to do coal mining. And so it's, again, named after, Shuffle just means shovel in German. Basically, Shuffle is designed to be a high-performance parallel shovel. It's just there to grab data out of Kafka and shovel it into Postgres as fast as possible. Now, we have roughly, during peak time, 500,000 requests a second. Those go into a callback queue, and we log whether we sent a callback or not. So 500,000 requests a second translates into 1 million messages a second that have to be logged. It's basically a universal data adapter. It shovels data from one to another. It doesn't have to be Kafka to Postgres. It could be Redis to Postgres. It could be Redis to Kafka. It could be Kafka to Kafka. We don't currently do Postgres to Kafka, but that could be added. The basic capabilities are, this is a multi-threaded application that can read from a source quickly. It can process it in parallel, and then load it somewhere else. Now, in the current implementation, I'll get to one very important feature that's under patch review right now, and hopefully will be committed next week. But currently, it just reads block of data from one place and writes it somewhere else. This is actually very limiting, and we are fixing this. So in the future, we will be able to read a block of, say, 2,000 JSON objects. We'll be able to pull attributes out, store some things in actual columns of a table, and store everything that we didn't recognize in a JSONB field. Current development, I mentioned we are working on unwrapping JSON. So what this means is we have a problem. I'll explain why this is a problem in a couple minutes. But basically we have a problem where it is very hard to generalize what we have right now. And so one thing we have to do to make it so it works on Postgres without any patches is we have to be able to change our indexing strategies a little bit. Part of how we would do this is we would do this by moving from a single JSONB column into something that looks a little more relational. To do this, we have to pull JSON objects out of the Kafka queue and effectively normalize them into something that looks a little more like a Postgres table. So we have a feature for that under patch review. There is a pull request. If you're interested in this sort of tool, there's the GitHub link. I would recommend taking a look, getting involved. It's a relatively small program written by in C by our system programmers and engineers, and it is one of the tools that we use everywhere along these sorts of data processing pipelines. So now that I have talked a little bit about Bagger's structure and Schaufel, I want to talk about some of the problems that we have actually run into in Postgres in this. This will become more important as I talk about the management tools we're trying to get ready to open source, but aren't quite ready yet. It'll also give you some really good ideas of what not to do if you're trying to build something like this yourself. The first one is partitioning limits. I'll pause after asking this question because I know translation and so forth, but how many of you have ever tried maybe hundreds or thousands of partitions and seen what the planner does? Anybody? Is it pleasant?
Not really.
Not really. We have not hundreds or thousands, we have almost 200,000 partitions. We tried querying the base table, the table that was partitioned, and we ran a query that would not hit any hours in our partition, so it would go through everything and it would exclude them all. And the planner took 15 minutes to conclude it didn't have to do anything. So there's some really big limits here. And so we tried querying the parent tables. That didn't work. We eventually set things up so that we would question these master servers where we should actually query the underlying data, and we actually made that work. So we pre-calculate that in our query program. We go out, we actually reach out to all these Postgres instances, query the data, and put it back together. The second major problem we ran into were indexing limits. Now, if we were to index all of the JSONB data in a GIN index, that would probably double our data size. We already have a ton of data. I'll go over the metrics at the end. But we want to keep the indexes down to about 10% of this. So what we do is we pull out about 40 sort of expressions that we index out of that JSON. It's a problem. Max index keys defaults to 32. So you cannot have an index with more than 32 sub-expressions, and we do this in Gin, right? It would make less sense with a B tree, but with Gin, it could make some sense. Max index keys gives problems, so we patched that up to 64. This is the first thing that we have to fix before we can help people implement the same thing exactly as we have it. Because how many of you really want to patch Postgres and build it yourself? Show of hands? Nobody? Oh, nobody likes the sense of adventure. So we have to fix this before all of our tooling can be fully released, because expecting that people are going to run things on patched Postgres is probably not very realistic. Second major problem is we run this on ZFS, which is a copy on write file system, which in English sometimes we call cow. Problem here is Postgres is also copy on write, right? So if vacuum comes along, it's going to update a page, and that page is going to get copied. ZFS will be very good at still doing linear writes, but your reads are going to get more and more fragmented, and since we're running this on spinning disk, that fragmentation is deadly to our ability to ever read anything out of this. Or frankly drop tables, which I mean isn't as bad, but that's still a problem. So we turned off auto vacuum globally. This turned out to be a kind of a bad idea. So the problem with this is, if you turn off auto vacuum globally, it doesn't really affect the data tables because we retain them for less than 30 days. They do not survive anywhere near a transaction wraparound anyway, so we don't have to worry about wraparound vacuums, right? But those aren't the only tables on the system. We have things like PG class, PG attribute, which are under heavy load because we are creating tables every hour, right? And those get really bloated. And we get transaction wraparound vacuums on PG class and PG attribute, which is a really bad thing, especially since now you're not dealing with a few megabytes, but maybe tens or even hundreds of gigabytes of system catalogs. That also means that system catalog access ends up becoming terribly, terribly slow. If you are typing a query and you press tab, you might as well go get a cup of coffee. Or 2 cups of coffee. Or go eat lunch. Yeah, that is very, very, very painful. I once just timed select, explain, analyze, select star from PG class. And I remember just that query took something like, I think something like 3 minutes. So the better solution to this would be put your main Postgres instance on fast storage like SSD or NVMe, create a table space on the ZFS, put all of your data files there, and disable auto vacuum individually on the partitions when you create them. Then you won't have this problem. Auto vacuum will still keep your catalogs nice and clean, but it will but it won't vacuum the tables on the copy and write storage. There's one other problem I wanted to mention about this that's not on my slide. And that is, if you have some things on copy and write storage like ZFS, and you have other things on much simpler storage, you can end up with cases where some things work really well and other things don't, or where maybe in a case of hardware failure, you have significant problems on the ZFS side. So it's something worth keeping in mind. Again, in our case, the data is important, but it's not critical. If we lose it, it's uncomfortable for our support department for about a month. After the month, we have new data in. nobody cares. But for that month, you know, it's not nice to go back to customers and say, yeah, I know you said you're not getting callbacks, but we're having some trouble pulling our logs and we can't look at this right now for you. No customer wants to hear that. So as I say, this is important, but it's not, I mean, if we lose the entire thing, it's not the end of our business. As a result, we did the other thing that nobody should ever do in Postgres. We turned off fsync. So having talked about our process 2 here, I want to talk about sort of where we are. As I say, we have a lot of the data loading tools released. You can go ahead and get involved. I also want to kind of make a suggestion that if this is an interesting topic for you, if you reach out to us, we're trying to get more and more of the orchestration around the system open source. But there should be enough information in this presentation that if you're trying to create something yourself, you can do it with Kafka and Postgres and the open source tooling that we do have. You may just have some more work on your side. The biggest problems we want that we need to solve are the production prototype problems. Elasticsearch was so painful for us that we took one sysadmin's 3-month prototype and we just put it into production and we didn't look back. As a result, we require patched Postgres. We require an expert team of people to keep this running. And it's not very space efficient. It's more space efficient than Elasticsearch was. But it's not very space efficient, and you don't want to go down the path we did and turn off auto vacuum globally. Just save yourself a bunch of trouble and don't do that. So we have to solve these problems first. They're not big problems. As I say, the first one, which is the requiring patched versions of Postgres, that requires that we add some functionality to Shuffle. And that functionality right now is being reviewed. It's in a pull request that you can actually go look at on the repo. And so that part's there. I think as we start to get the rest of the tooling up, people will have better ideas of how to make it easier to run. Maybe we'll get more involvement, and that will be easier. Fixing auto vacuum, we know how to do it. We are working on it, and it's just a matter of fixing a little bit of automation here and there. So the good news is that these are actually not giant problems, and we're working on them. We expect them to be fully out as it is, and basically that means that the programs that we have that say load what is in the backend to, new Postgres instances into the master databases would then be able to be just used as is. The second problem, which is actually also not a huge problem, is a generalization problem. This was a prototype. It was shoved into production very quickly. As a result, there is a very tight coupling of the implementation to our business logic. So basically what we have here is, all the indexes are hard-coded, things like that. That just needs to be moved out to configuration. We actually already have that in peer review also. I was very much hoping to be able to stand up here and say, yes, we are releasing this today, but we probably need another week on that. Maybe a month if things continue to go sideways. And we have to do this in a way that's backwards compatible. We know how to do that. It's not the end of the world. And then we have just a few more questions we have to ask, probably other users. For example, with Elasticsearch, we had a very major problem. When people would query Elasticsearch, if they queried a very big, large amount of data, what would happen is they could exceed the Java heap. Elasticsearch would crash. The client would go, oh, retry logic. We are going to try this again. It would repeat on the next node. The next node would crash. It would repeat on the next node. The next node would crash. Eventually you'd lose quorum and we would have to restart the cluster, which would be extremely painful. So one of the decisions we made, which we need to revisit, and I'd be happy to talk with people outside of this, whether you have opinions on this, is we actually check the plans before we execute, and we refuse to execute a query that does a sequential scan. Probably makes sense to keep that in because our system is heavily optimized for basically large linear writes. And so when you try to do a large linear read, it is very, 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 very slow. However, maybe other people have different use cases, and maybe our case is too general. So this is something we have to discuss with people, and we have to revisit. Probably, you know, either you know, in the course of the first release or something like that. So here's how big our cluster is at the moment. We have 80 servers. Each server has 8 to 10 Postgres instances on it. We checked, we have 740 8-terabyte hard drives, each running ZFS. And each one of those hard drives is also running the storage for a single Postgres instance. So we have 740 Postgres instances storing this data. We are able to load sustained over 1 million data points a second. And we store approximately 17.5 petabytes of data. We shoot for a 30-day retention. We usually don't get there. I think we're right now at somewhere like 28 days. But that changes. When we run out of disk space, we drop oldest, and we go forward like that. So, what we expect, so what we really learned from here was be very careful with ZFS and Postgres, especially under very high load. Copy on write, under copy on write is painful. And there's simply no way around that. And at least with ZFS, I don't believe there's a way of getting the compression that we need without having that copy on write overhead. Compression is important because hard drives spin, they are high latency. But if we can compress data, we can increase the throughput of our writes, right? Secondly, please don't turn off auto vacuum globally. There is simply no situation where this will end well. By all means, turn it off on short-lived tables that are maybe going to be very big, where you don't need index-only scans, and where auto vacuum is causing more problems than it helps. But do not turn it off globally. You will get yourself into a world of hurt relating to your system catalogs, in particular, your stats tables, your PG attribute, PG class, I think are the three single biggest ones. So with that in mind, I'd like to invite people to reach out, and I'd like to take questions at this point. Any questions?
Well, I will be the first then.
Okay.
You mentioned that you have you discard the queries
Yes.
which plans sequential scan.
Yes.
How do you achieve that?
So we have the query program, which actually goes out. It takes in command line arguments for what you're searching for. It goes out. It then figures out the queries that it's going to run, and it runs an explain on every Postgres instance where you're going to actually retrieve that data. And it checks the explain for sequential scans. Right now, again, production prototype, it pulls back the textual representation of the query plan and searches for seq scan, which is maybe not the best way to do it. I would recommend using JSON format and looking through it that way instead. But that's the way that this was done. And then in the event where you see a sequential scan, what it then does is it delivers a warning to the user, because if you're trying to track down callbacks, and let's say those callbacks are going to a very big customer, and you probably want to know that the data you're looking for isn't complete. Because otherwise, you'll say, hey, you said you only got 80,000 callbacks, but I can only find 10,000 in our logs. You know, customers will be even more unhappy if you do that, right? So that's that. And then we run the queries, we get back JSON, and then we basically append them together into the standard output of the query program.
Thank you.
Yes.
Thank you for your report. One question: why you use Postgres, and have you tried another database, ClickHouse, for example?
So this was put into practice 2 years ago. We did not think at the time ClickHouse was mature enough. It might be now, I don't know. I have looked at ClickHouse a bit. With the log tables, maybe not. But we chose Postgres after evaluating a bunch of different options. We looked at Cassandra, we looked at ScyllaDB, we looked at a few others. We chose Postgres basically due to 3 things. The first is that we knew it well enough that we could put it into production and expect that we could keep it running. And when you have terabytes and terabytes or petabytes and petabytes of data, that's kind of important. We also looked very closely at disk I/O utilization. And what we saw with, for example, Cassandra, was that we had twice as many IOPS for the same data load in Cassandra as we did in Postgres. So Cassandra would not have scaled for us as well as Postgres did because storage and disks are bottlenecks. So those were basically the 2 major reasons. We didn't fully optimize things as well as we could have. Again, JSONB is not a very efficient storage technique. But we did, do some basic testing there, and what we found is that if we turned off compression on that field, we could effectively use ZFS to compress it much better on the block level, and that would improve our disk access more. So we tried a bunch of things on a bunch of different databases, and basically this is where we could find the best the best sweet spot in terms of load performance for us.
Well, hello, thank you for your talk. Actually, I have the same questions. We the happy guys that have a production Postgres database on top of ZFS already, and we don't have possibility to move to anything else now. Mm-hmm. So would you please go a little bit deeper into tuning performance with ZFS and Postgres,
sure.
Please?
So there are a couple of different things that happen with ZFS. ZFS, as I mentioned before, does copy on write, which means you need to do everything you can to try to avoid a normal vacuum. You're actually much better off to do vacuum full if you can afford it than to do a regular vacuum, because this will then do a full linear write of the table. You'll get a new file, hopefully in linear space. I guess I didn't quite get from your comment whether you're using ZFS on spinning disk or whether you're using it on SSD. If you're using it on SSD, that consideration isn't quite as...
Yes?
Is it?
SSD.
Okay. If you're doing it on spinning disk, you really have to worry about those issues because the file fragmentation is going to kill your read performance, especially because Postgres assumes that a sequential scan of a table is mostly linear I/O, and if you have things tuned for hard drives, you're going to the planner is going to assume that that the disk I/O is much, much cheaper than it actually is. The second thing is you need to make sure that your block size matches your Postgres block size. By default, your Postgres pages are 8 kilobytes long, and so you should use the same in ZFS so that when you write a page, you're not amplifying things. If you were to say, choose a much larger block size, let's say 16 kilobytes or 32 kilobytes, then if you write 8K, you're going to read 32K or 16K or whatever, and you're going to write that. So that's going to hurt your performance there too. So you need to align those considerations. Postgres writes pages, and so you should try to make sure that that ZFS is going to handle things the same way. The third thing is you want to pay very close attention to, if you're using compression on the file system, pay very close attention to the impact of the particular compression algorithm you're using and actually benchmark different ones on your use case. The reason is, with compression, you are trading disk IOPS for processor time. And depending upon your workload, you might have wildly different trade-off points there. So those are the three biggest things that you have to look at. And then I guess the other thing is, a lot of other things, standard things like make sure your wall's on fast storage, make sure that if you can make sure that your indexes are on SSD, if you have anything else on HDD, make sure your indexes that are there are on SSD, and just a number of other basic things. But those are at least the things I know of that are most important. I guess if you're using SSDs, you may also want to take a close look at making sure the SSD block sizes are aligned with the ZFS block sizes, so that you have nicely harmonized writes all the way down.
So I will take next. Do you consider using larger block size in PostgreSQL instead of 8 kilobytes, like 64?
Yeah, we've thought about it. The thing is, what we would have to do in this case is we would actually have to set up a bunch of servers and benchmark them. And while we've thought about it and discussed it, it's mostly a question of nobody having the time to actually set up the benchmarks and see if it helps. My assumption is that it probably would. And we would probably do better to increase the block size up to the maximum, just because since we're relying on ZFS to do compression at a block level, having bigger blocks should improve the compression ratio. So we believe it will, but we haven't had time to benchmark. Again, the downside of that is that if we want this to run on a vanilla Postgres out of the box, we probably don't want to be telling people to go change the block size and stuff like that, because that's a compile time setting. And
You're already patching Postgres. You're already patching Postgres.
Yes,
so why not?
Yeah, we also side stream in patches from upstream. We side stream our own patches when we fix bugs. We're comfortable doing that, but as we're trying to get things out to everybody else being able to use it, insisting that Debian users go out and patch Postgres is very different from insisting that Gentoo users go out and patch Postgres. We're using Gentoo, and so it's real easy to side stream in these patches. But for people in a lot of other distributions, that's not the case, right? So if you're using CentOS or Debian or something, chances are you're going to want to use official binaries either from the Postgres developer group or from your distribution or things like that. And so while we might still do this, we probably wouldn't make it as a general recommendation. So.
Thank you.
Any other questions?
Any more questions? Ну что ж, я думаю,
Okay, I think thank you all very much. Thank you very much to our presenter. If any of you have questions or if they just appeared, then you will have the opportunity to catch him on the floor and to ask him the questions there. Thank you.